Hello everyone, welcome back to the next lecture, which is lecture number 2 for SOM. And in this lecture, we are going to see the stress strain curve and the engineering properties of the material. So let's start with the recap. So till now, we studied uh, we studied about stress and strain, and we got to know that stress is nothing but P upon A, and strain also we knew that is change in length upon original length. So now we know that how to calculate stress separately with this formula, and how to calculate strain separately with this formula. But now we need to know, is there any relationship between them, and if it is, then what relationship is there in between of them, right? So in today's lecture, what we are going to do is this: we are finding out this relation between stress and strain. So here we can see the experimental setup, and that we are going to use to calculate or to plot the graph between stress and strain. So there, the experiment setup is something like this: that we have universal testing machine, we call it UTM in short. Okay, so what we are going to do, this is our specimen, so we will be placing this specimen between the machine. Okay, now we'll be applying the tensile force gradually. So the specimen will be pulled from both the sides. Okay, and we will be noting down how much pressure, how much of force we are going to apply, and we'll have the original area. Okay, and then we'll be just noting down the force which we are applying. So due to some time, so after some time, due to this force, this material will stretch, right, and the cross sectional area will reduce, right? So due to the force, the stretch will be there, so they will be, this is original length, and then we will be having elongation also. So from that, so we are applying load, right? We can convert this load to stress divided by original area. So load divided by original area, we will be getting the stress, right? And then we will be converting the elongation to strain. So elongation, we have delta L divided by original length, so we will be getting the epsilon, that is nothing but elongation. So at each and every point, right, we'll be applying force and we'll be seeing what's the strain, right? So we'll calculate stress and we'll calculate strain. So strain will be on x-axis, stress will be on y-axis, because strain is the independent variable that will come, and stress will be dependent on that. So uh, with each and every strain, we'll be plotting how much stress was generated. So and then we'll be doing it up to the point where material breaks down. So we'll be having rupture or fracture in the material. So up to when we will be plotting this value of stress and strain. So for different materials, the graph comes out to be different, right? So this is universal testing machine, and this is what UTM test is doing. So though so from here we can say that this stress strain curve is not theoretical, right? It's not theoretical that we plot. It's a representation of how real materials behave when we increase load on them, specifically tensile load. So the different materials behave, that behavior is plotted here. So this is not theoretical, right? Now let's move on to that, why do we need a stress strain curve? Okay, so we should ask few questions, right? Like, does deformation increase proportionally? That we are applying tensile load and the material is deforming, so is the deformation is proportional to the load? So deformation is proportional? This is the one question that comes to our mind. And then another question that comes is, does the material return to its original shape? So if we remove the force, can the material come out to its original shape? So regain original shape, is it possible? That also we check. So, and also the question is that at what point does permanent deformation begin? So after, like, we are seeing that can it regain its original shape, but there will be a point after that the material will not come to its original position. So that is permanent deformation. So permanent deformation when? So when was the permanent deformation started, right? And then one more question we can ask, that what does the material when the material finally failed, right? So when failure happened. So when does the material finally failed? So these are the questions that are answered by the stress strain curve, right? So the stress strain curve answers all the questions. So now let's see the first testing curve that we plotted for mild steel. Okay, so for mild steel, what we are plotting between engineering stress and engineering strain. All right. Okay, so as you can see, yeah. So as you can see, so at y-axis we have engineering stress and x-axis we have engineering strain. And then we can see that there is elastic limit, there is proportional limit, there is upper yield point, there is lower yield point, and then we have yield plateau, then we have strain hardening region, and then we have ultimate tensile stress, and then we get neck-in region, and then fracture happens, right? So these are the points that are there under mild steel. So we'll be explaining it separately, but this is how a mild steel stress strain curve looks like. So this entire curve represents the life story of a tensile specimen from the beginning of the loading until the fracture, right? So from the beginning of the loading, it was somewhere like this, the stress, and then at the fracture, the stress was somewhere like this, and the elongation was somewhere like this. So it's a entire life story of a mild steel specimen that was tested on the UTM, right? So let's move on to the next slide, which is the very first region, that is region OA. So from O to A, this is region OA, right? So in this region, we can see that this region is fully straight, right? So it's straight region. So in this, why it is straight? So we have to see that. So as the stress increases, so that means here we can see that stress is directly proportional to strain, because it's linear, right? And it's linearly increasing, so it's directly proportional to strain. Therefore, can we say that if we remove this proportionality sign, we get equal sign, and then we can see it's E epsilon, where E is Young's modulus. E is what? Young's modulus. So it is nothing but it's a constant that came when we removed the proportionality sign, and it's nothing but it's slope of linear region, I can say, right? So it's nothing but slope of the linear region or linear portion, we can say. But also we can see that A large E does not mean a stronger material. It means the material is difficult to deform elastically. That what does it mean? That if it has more E value, okay, E is more, then we can say that it will be very difficult to deform it elastically. It will again regain its shape, right, easily. So if E is more, it's more elastic. That means if we want to deform it, we have to apply more stress or more strain to it, then it can't recover. So if E is more, the stress generation will be recoverable. Okay, so this is what does this mean. It doesn't mean that it's a strong material. For example, we have rubber, elastic. So its E value is very high. We can stretch it very long, right? But it's not a strong material, right? So this is what large E does mean. And now let's move on to next slide, which is proportionality limit versus elastic limit. So in this graph, you can see this is proportionality limit, this, and this is elastic limit, right? So up to OA region, it's directly proportional and elastic, but up up to B, in region AB, it's still proportional, right? But it's not linearly proportional. Okay, so if we see, so proportional limit is up to this point, we can still say that sigma is directly proportional to epsilon, right? It's still proportional. But at an elastic limit, if the load is removed, the specimen returns completely to its original dimension. But in proportional limit, they the specimen will not come to its original position. There will be a little bit of deformation will already always be there in proportional limit. But in elastic limit, material comes to its exact original shape and size after load removal, right? So uh, so let's see the next slide, which is what happens when we cross the elastic limit. Okay, so before elastic limit, we are applying load, it's deforming, and when we are unloading it, then we will get the original shape. This is what elastic limit is. But after elastic limit, we can see that load will create deformation. Then if we do unloading, there will be a little bit deformation that will remain there. So that deformation is permanent deformation. It can't be recoverable. And this is the deformation which we call as plastic deformation. This permanent deformation is known as plastic deformation. Okay, so now uh, so this plastic deformation is a thing which we can say that it's not simply a large deformation, it's a permanent deformation. Plastic deformation is, uh, people get confused that plastic deformation is large deformation. No, it's simply a permanent deformation, right? So it's not necessary that it is a large deformation, but it's permanent. After that, it will not be like, this is the point where it will not be recoverable, right? So this is what plastic deformation is. Now after you see the proportionality limit, then you come to the yielding in the graph, right? So you see upper yield, lower yield, and then you see yield plateau, right? So let's see what's that. So yielding in mild steel comes with upper yield point, and then there will be sudden drop that we call lower yield point, and then we have yield plateau. Okay, so I want to ask a question, that why does material suddenly deform significantly without a corresponding large increase in stress? Like you can see here. So you can see here you can see there is upper yield point, there is lower yield point, but after this you are not increasing the stress, right? You are not increasing the load. The load is somewhere in this region only, but without increasing load you are seeing there is a lot of deformation going on. Initially it was here and then it was here, right? So this is yielding region. This creates yield plateau. Yield plateau is nothing but stress remains almost constant while strain increases considerably. Okay, and what is the upper yield point? It's the highest stress at which yielding starts. Okay, so it's the highest stress, and lower yield point is the large plastic deformation occur with drop in stress. So after this, you see lower yield point will be the point after which the yield plateau starts. That means there is no stress increase, but deformation is going on, and going on. Right. So this is what yield plateau is. Right. So the question which we have, that why does mild steel have yield plateau? So we have dislocation movement, and then we have resistance to plastic deformation. So there is where resistance will be there. So now let's see next, which is strain hardening region. So after you see the yield, right? Now you see after the yielding finishes, there is strain hardening or work hardening. Now what is that? So after yielding, we get to see that stress starts increasing again. Okay, yield complete, and then stress will start increasing again, and then the material that has already undergone plastic deformation, yet more stress is now required to continue deforming it, right? So you see here it's already deformed a lot without increasing the stress, right? But now after that point, after full yielding region, it requires a lot of stress to gain the uh, deformation. It requires a lot of loading. So this region is known as strain hardening region. So now it's not strain is not happening very easily. So that's why we call it as strain hardening region. So yet more stress is now required to continue deforming it. So uh, more stress is now required to continue deforming it. So yield will give plastic deformation, and then we have strain hardening region, right? So yeah, so now we come to the ultimate tensile stress. So here you can see after the strain hardening region, you will get the point where the stress will be maximum. So the material will take maximum stress, that we call it as ultimate tensile stress. So it's nothing but we can calculate it basically. So calculation is like if I want to write down the formula, sigma u is the ultimate tensile stress, and it is nothing but the maximum load it took, right? And the original area. So the area which was initially there, that we call it A naught, original area. We don't take the current area, true area we call, right? So we have to take the original area because it's engineering stress. It's not true stress. So yeah. So engineering stress uses original cross sectional area. So this is A naught. Okay. So if the specimen reaches maximum load here, why does the stress curve subsequently fall? See, we have seen that we got maximum loading it's bearing here. Now it's getting dropped, right? So this dropping is known as necking. So what's necking? So after UTS deformation is no longer uniform. Okay, when the material reaches the ultimate tensile stress, deformation is not uniform. So because there will be reduction into the area, the localized area. If I zoom it, yeah, So if you see here, what's happening during necking. So after the specimen reaches ultimate, that means maximum load, uh, it's the deformation will not be uniform after that. So localized region begins to thin. So this is the area you got the maximum load. It's still like in this case, the load is still less than maximum. Load is still less than maximum. Okay. So what's going on after a bit? The region will start becoming thin and we call it neck, right? So the area at the neck reduces continuously and load carried by the specimen will decrease, right? So this is the maximum load it took, okay, after at UTS. So before UTS it was taking P load. At the UTS it took maximum load, and after that the load that it is able to take will be less than the Pmax, and area will also start reducing. So we call it necking, and then necking will be more and more prominent. So that means it will reduce further. So the neck will become more prominent and it will get reduced. And then after that there will be fracture. So engineering stress P upon A naught decreases because load decreases and we still divide by original area, right? So we are still dividing by original area. Formula is P upon A naught, right? A naught we are just not changing, but the load which is this specimen is going to take is lesser. So engineering stress will decrease. That's why the graph comes down. So here you can see this is engineering stress, and then you can see that it decreases. So it decreases, and this region is known as necking region, and it will go up to the point of fracture. So it just starts after UTS. Deformation becomes localized. Cross sectional area at neck reduces continuously, and load carrying capacity decreases, and it leads to the fracture of specimen. So let's, yeah. So this is what necking is. So after necking, you have fracture, and that's breaking. So this is the final uh, point where it breaks. So uh, so the question this is, why does engineering stress decreases after UTS? Okay, this I already explained, because we are dividing by original area, and this is the reason engineering stress and true stress are different. True stress is nothing but true stress is sigma is equal to P upon A. Whatever the area is there at that time, that only we have to put. But engineering stress is P upon A naught. So the original state area that we considered, that only will be taken as the actual area in the case of engineering stress. So this is a limitation there. We can't we can't just measure area at each and every point, right? So we have to do a bit assumption there. So we can't. So we have taken assumption of area should be original one that we took. Now we have engineering stress versus true stress. So it uses original area, it uses instantaneous area, the area at that particular time, AI, and it's convenient, right? But it's more representative of actual stress. So due to convenience, we choose engineering stress, right? Because area measurement is not that we are going to do again and again and again thing. So this we reduced our efforts in that. So that's why we use engineering stress. Now we see true strain. So let's increase this also. So let's understand true strain due to finite incremental loading. So we consider a uniform bar of original length L naught and its area A naught, and it is subjected to tensile load, right? And then bar elongates by several small increments like dA. So this was the original length L naught, and then it elongated with dL1. right? So L1 is this, and then this elongated with dl2, L1 plus dl2, and then similarly li minus 1 or 2 dl, right? So this is was increment was there. So after nth we can say L naught plus summation of all dli is equal to 1 to n, right? So this with this we can say that now the true strain is how can we derive that is let's consider a very small elongation dl. This is the dl. At any stage L is the length. Okay, so incremental true strain at any stage will be dl is equal to dl upon l, d epsilon is equal to dl upon l. So if I integrate for this from L naught to L, right? So initial length was L naught and the final length which will be L after increment, after the full effect of the load that was applied, right? Then it will be L. This is L, right? So if I integrate it from L naught to L, dl upon L, so we get ln, right? So ln L minus L naught. So my true strain comes out to be epsilon t is nothing but log of L upon L naught. So this is a finite elongation from L naught to L. It's not infinite. It's because of the effect of the load, and it is the deformation is finite. It changed from L naught to L, so it's L upon L naught. So this is true strain. Okay, this is true strain. Now engineering strain is nothing but, so let's move myself a bit. So if we compare it, the engineering strain versus true strain, I get to see that engineering strain is based on original length, right? But true strain can be calculated by this formula L upon L naught, and here we can see that del L upon uh, L naught. This is engineering strain. So if I want to see some points, which is, see, true strain considers the change in length at each instant. Okay, change in length at each instant we are considering, but engineering strain uses only the original length. And for small deformation your true strain will be equal to this engineering strain only, because you are not changing that much. And but for larger deformation, true strain will be much more accurate, that we are going to calculate in comparison to engineering strain. So this is how we see that, yeah. Now we have a question that does every material has the same curve, like mild steel, high grade steel, aluminum, copper, brittle materials. So do all those have the same curve that we saw? No. The answer is no. So every material has different curves. Okay. So and every material curve was made by testing it under the UTM, Universal Testing Machine. So in that only we applied tensile stress and we noted down up to which extent the stress and strain values were there, and we plotted those. So for each and every material, the different stress strain curves come out to be. So basically, we can simply say it's nothing but it's a fingerprint of material behavior, how the materials are behaving. So let's say mild steel versus high strength steel. So you can see you have this red one is the mild steel curve. Okay, it is mild steel curve, and the blue one is for high strength steel. Okay, so for mild steel, you got an upper yield, you got a lower yield point, and then you have a yield plateau, right? And then we have strain hardening region, then ultimate will be there, and then fracture will be there. But in high strength steel, you will not see uh, a proper yield point, right? So distinct yield point will not be visible here. You can see ultimate stress and then you'll be having fracture, but no yield point was visible when high strength steel was tested. So no distinct yield point and yield occurs at a higher strength. Okay, and but see, you in this region at any point the yield can be there. So here the yield occurred at lower value, but here the yield can occur, definitely is occurring more than that value. The yield strength for this came approximately to 50. Okay, and for this the yield strength came about in the range of 500 to 700. Okay, and ultimate tensile stress comes out to be in the region of 450 to 600, but its ultimate tensile stress is this much, 900 to 1200. So that's why it's high strength steel, because it can bear the stress up to bear the loading up to very high values. These are in MPa, so the that's why it's called high strength steel. But deformation will not be that much, right? So it fractured uh, in uh, in this much elongation only, but mild steel can fracture at higher elongations. So strain hardening region in mild steel is also, it's very pronounced, but in this strain hardening region will be present, but it will be very short. Okay, and ductility for this it's very high because it has very high elongation, but here its ductility is low. Toughness, it's tough. The So you can see the toughness, toughness is nothing but toughness is area under the stress strain curve. So area under the stress strain curve for mild steel is larger, and for high strength steel it is smaller. So this is how when we get the comparison between mild steel and high strength steel curves. Okay, now let's move on to the next curve, which is in between aluminum and copper. So this also you can see there is no distinct yield point or something in copper as well, but we can see that copper has high ultimate tensile strength, and aluminum aluminum has not. So we have these values. Comparison, you can study, read it by yourself. It's I'm just showing you the graph, the difference between the graph. So for every material you can see there is a different graph. Okay, and then we have ductile and brittle material comparison. So ductile, mild steel is very ductile, and but brittle material you will not see elongation that much, and there will be no distinct yield point, and deformation, all the deformation is like almost elastic. This we have to keep it in mind. And fracture occurs suddenly, we will not have a little or so warning there. So for example, brittle materials are concrete. So it if it is cracked, it can suddenly fall to our head. So concretes are very uh, um, we can say unexpected in terms of tensile loading. No plastic deformation, very low ductility, very low toughness, so small area under the curve, right? So this is what the comparison between ductile and brittle material. Now we move on to the material properties. Let's reduce the size to original. Yep. So this stress strain curve does not tell only about how the material deforming, okay, how the material deforms. It also shows the several important material properties. Okay, so the very first, like some properties are like elasticity and plasticity. So elasticity is the property which is ability to return to its original shape. This also shows in the stress strain curve. Plasticity is the ability to undergo permanent deformation without immediate fracture. right? So this is also a very important term that we should understand. And then it also shows the ductility and malleability. So ductility is nothing but tensile deformation. So it is able to undergo significant deformation in tension before fracture happens. Okay, so we commonly measure it in percentage elongation and then percentage reduction in area. And whereas malleability is what? It's the deformation under compression. Okay, ductility is deformation under tensile stress, malleability is deformation under compression. So that is nothing but ability to be rolled or hammered into thin sheet, right? So this is malleability. And ductility and malleability confuses sometimes, so you have to understand in tensile deformation ductility, and in compression the deformation will be known as malleability. And then we have resilience. So resilience will be directly connected to the area under the curve. Okay, so resilience is nothing but ability to absorb energy elastically, ability to absorb energy elastically. So it's the area under the stress strain curve up to elastic limit, right? So the elastic limit, that means the OA region was there, right? So the area under that OA region will be your, if we calculate it, it will be a resilience. Okay, so let's say UR is the elastic energy per unit volume. Okay, so this much is the elastic energy for per unit volume. So for linearly elastic material, the UR will be sigma y square upon 2e. So this is your resilience. Okay, so if yield stress is taken as elastic limit stress, so yield stress is taken as, this is sigma y is nothing but yield stress. So only if yield stress is taken as elastic limit stress, then we will be uh, telling that UR will be nothing but sigma y square upon 2. Now we have toughness. So resilience is nothing but energy which is absorbed elastically, and toughness is the total energy which was absorbed before fracture. So graphically it will be the entire stress strain curve wala area. So it will be the entire area under the stress strain curve up to the fracture, right? So resilience is up to elastic limit, toughness is up to fracture, total area. So toughness is the energy which can be absorbed up to fracture. Resilience is the energy which can be absorbed up to elastic limit. So this is what toughness versus strength versus stiffness. These are also some of the terms. So strength is how much stress can it withstand. Stiffness is how resistance it is to deformation. So if deformation is there, how much it can resist that deformation. And toughness is how much energy can it absorb before fracture. And ductility is how much plastic deformation is there before fracture. So these are some of the terms that we need to know how to distinguish between them. Right. Now we have fatigue. So fatigue is what if the stress is repeatedly applied and removed. So stress is applied on the body, it's removed, and then it comes back, and then it is removed. So cyclic loading we call it, right? So due to the cyclic loading, application removal, application removal, application removal, the fatigue will be there, and due to that, the object will be uh, failed in fatigue. So material may fail even when the stress is below its static strength. So if, even if you are applying lower stress, but you are applying and you are loading it with that lower stress and then reloading, load and reload, load and reload. Then if it is, even if it is very low, material can fail into the fracture, fatigue, right? So yeah, and then we come to creep. So creep is nothing but uh, if the material is continuously loaded for a very long time. So if material is loaded for a very long time, where if it fails into creep. So the strain that will be generated, the strain will known as creep strain. Okay, so with the time it increases, right? So we have creep of three type: primary, secondary, and tertiary. And so primary is immediately after loading. Secondary is creep strain increases at approximately constant rate. So it will be increasing with the time. And then tertiary is creep strain, creep rate will increase, but not proportional to the time. Okay. And it is caused by damage accumulation such as voids, micro cracks, and necking. And after that, it will be like increased, right? So this is what creep strain is. Now, next we have hardness. So hardness is nothing but its resistance of a material to localized permanent deformation. Resistance to deformation is known as hardness, and this also you should know. And then we have tenacity and viscoelasticity. Elasticity. So tenacity is the ability of material to withstand loading without rupture. Okay, often discussed in relation to toughness and strength. So tenacity is the ability to withstand loading without rupture, and viscoelasticity is exhibit both elastic and viscous behavior. So for example, we have polymers and biological materials. These exhibit both. These have elastic behavior as well, and they have viscous behavior as well, right? So we call it as viscoelastic material. And then we come to the final conclusion, which is many properties and there is single curve which is showing them. So slope which will show you stiffness and Young's modulus. Yield will show you yield strength. Maximum stress will show you ultimate strength. Plastic region ductility. Area to elastic limit resilience. Area to fracture toughness. Fracture point will be the failure. So you are getting it. So we have only single curve and it shows so many material properties. That's why in material science or science of we are the subject we are studying, strength of material, this stress strain curve is very important. We can get the idea of so many properties related to that material just by seeing that one curve, right? So that's it for this lecture, I guess. And yeah, I have some questions for you. You can answer it perhaps in comments. That is proportional limit the same as elastic limit? Now if you have listened to this lecture very carefully, you know the answers. Can a material have high strength but low toughness? Tell me. Why does engineering stress fall after ultimate tensile strength? And why is 0.2% proof stress used for some materials? And which area of stress strain curve represent resilience? So these are the questions that you can answer. And then with this we have the summary. And in next lecture we will be seeing. Okay, so in this brittle fracture also we have a bit that brittle fracture will not show you any warning. It is very small plastic deformation. Then we have sudden failure, and then we have fracture behavior. So high strength does not automatically mean that there will be safe behavior. So this slide I guess we missed in between. So we have the lecture summary. So we have from loading to fracture, we studied everything. So with this we complete the stress strain curve analysis. Now we'll see let's what we study in the next lecture. I hope you understood this, and thank you.